Okay, guys, we can get started now. It's 10 past. Honestly, who read them? Okay, 1, 2, 3, a little bit, one over there. Yeah, it's like the same papers as last week and one additional paper on efficient backprop. Like efficient backprop. All right. So, do you guys have any questions about those papers? Yeah.
So, in the 98 piece, it's talking about the last RBF layout.
Which page is this?
I identified it.
Oh, okay. All right, anybody? Maybe we can answer a different question at the same time.
So it's around page 9. It's mentioned in page 9, but it says that the weights of the RBS are fixed. Otherwise, there's a collapsing phenomenon.
Here or here?
So page 9 on the bottom on the left side, just below equation 8.
To adapt, we allow the parameters to adapt. Equal.
So the solution for the collapsing phenomena is not to allow the RBF weights to adapt. And
oh, okay. So this has
I don't understand.
the collapsing behavior. Yeah, it's related to the energy-based learning tutorial.
Yes.
And it has something to do with like the collapsing of the energy function.
You don't take the most
offending answer.
Yes.
Yeah, if you have something that is kind of if you don't use a contrastive term in your loss function, okay, then you can have the case where basically two functions learn something that have nothing to do with the input and the output.
Okay. So the solution here is not to use a different cost function, but it's just to not allow the RBF weights to change at all?
Yeah, I guess so. I mean,
and then turn around?
If they are not allowed to adapt. Yeah. So basically you just make a fixed function out of it. Okay. Any more questions? Yeah.
From the energy-based learning,
yeah,
page 29, so the condition 3, like I understand condition 1 and condition 2, what they say about the prediction and like the energy of the correct.
So wait. Page 29.
No, I mean the energy-based learning. The other.
Oh, this is the wrong one, yeah. Oops. There we go. Right.
Yeah, I'm a bit lost here with the half planes, the HB1 and I don't know exactly.
Mm-hmm.
I'm losing it. And with the graph, like what are those things that the EI is the correct one, like the error one, and EC is the correct one? How is it lab?
So in the surface of the loss function should be such that there exists at least one point in the part of the feasible region intersecting the half plane such that the value of the loss function at this point is less than its value at all the other points. Yeah, this is definitely like the hardest part of the paper.
Yeah,
and
here I got both of those. The HB1 and HB2, like how did this come up and what do they actually mean and why do they intersect?
Yeah, if to give you a really good explanation of that, I'll probably have to spend a bit more time on this, I have to honestly say. It's something that Jan is going to talk about in the next few lectures. the idea was that you guys get some introduction to this now, get used to the language because he's going to use it, and because the language comes up all around his teaching. Because there's many other things on the agenda, I'm going to write this down and we'll do it at the end of the class, if you don't mind. Okay, any other questions? All right, next question is if I think people have problems maybe with Mercer or HPC, there's just too much being used. People have problems getting jobs, or like too many resources are being used. Jobs just take too much time to run. Is that true? You guys have like a hard time sort of dealing with all this stuff. Who here implemented the GPU optimizations? The GPU optimizations. So actually making use of like the batch processing of the forward and doing all that. Yeah. So if you did not do that and you're doing GPU computations, you should really make use of that. I was planning on going into that a little bit more today. The next thing people may not be too aware of is what this CUDA call actually does. So if you have, if you're calling CUDA on a tensor, what it means. Is anybody confused with respect to that? Because it actually means that the tensor is going to be put on a device, right? So if you take your entire training data and you apply CUDA to it, the entire training data is going to be on the device and it's going to take up a lot of RAM. All right, okay, so people are not confused with that.
But if you want to do an operation with a CUDA tensor and just a number, so can you just, so it's not scale up. I got an error that you cannot do one scale in the CUDA tensor.
Yeah, you have to use the multiply function. You have to use like multiply and then put the scalar in here for the tensor. Yeah.
What he says that we were trying to use the tutorial code where the training happens on every sample because it's stochastic gradient.
Mm-hmm.
And the CUDA code was throwing an error because it was saying that output is a number, not a tensor.
I don't know what code you're talking about exactly.
I'm talking about the initial code from the tutorial.
Oh, yeah.
That code we couldn't run in CUDA.
That's code is bad. The CUDA from
Do you mean this?
Yeah, because it says that
Right here?
yeah, the target size is a number.
The target, this one. So targets.
He was expecting something like a CUDA thing.
Right.
I don't think we're reading this code with CUDA.
Yeah.
You should probably, I mean, as is, this should run on CUDA. My recommendation really is, and that's kind of like part of as you go along, is so first of all, if you got this code, you should have probably like read through it and try to understand every line to some extent, to like played with it. And then now, I think a good idea is to just, delete these things and write them yourself from scratch, actually making use of the mini batch as a tensor and doing the indexing and so on as a tutorial code. Yeah.
So you're saying mini batch is a tensor, you're just meaning that little 4 item or one.
Yeah, you don't need to.
That is an entire input instead of
Yeah, exactly. Don't do these for loops
yeah.
because that's going to take a long time. You can just do that in one forward call and one backward call. And that will also get rid of these divisions. Yeah. Yeah, and I think that's been a problem for many people. So if you want to understand why, if you go to the actual implementation and you look at update output, there's one case where dimension is equal to 1, right? And then there's one case where dimension is equal to 2. So when you look at the case where the dimension is equal to 2, and there's another sub-case for the output dimension, or the bias size, yeah. it just does an add multiply, right? So this takes the input and adds to it the weight, which means I think in the criterion it's then going to be treated as like a single thing. Actually, not entirely sure on this. I should know this better. Right. So the gradient that you're getting back from the criterion doesn't have to be divided because it's just this big matrix. It's not accumulated across the photo. It's not really clear the way I'm explaining it. Okay. So yeah, make use of these optimizations. Make sure that you're using that without the for loop, and it's going to make your code a lot faster. Make sure you don't put stuff on a device that you don't need at a particular time, so only put the mini patch on a device. Don't put the entire training data on it, because some people I think have problems fitting their model onto the device, and at this case, unless you're doing something very, very advanced, it shouldn't really be the case, I think. Yeah.
Is there a command to tell the GPU that it can remove whatever it is from memory? Or
Remove?
Does it do so automatically?
Oh, I see what you mean. Like you want to clear the entire device
Or I mean, like, let's say you have a model and then you want to train another model on the same.
on the same thing.
You could set it to nil.
You set it to no. I think if you change the type back to float, it may take it out of the device.
Okay.
I'm not too sure on this. Yeah. So you want to do multiple models within like one
Yeah.
interpreter, sort of, within one run of it. Yeah. Another thing is also some people are running like multiple processes on the same GPU. So you have like Lua, and it's all running on the same GPU. That's not a good idea. Because what it does is every time you're running like a process on it, there's going to be some set of data and kernels on the like kernels of functions that are on the device. And these functions are associated to a particular process. And the GPU is going to try and give all these processes like a fair amount of, time or resources. And it's going to incur a context switch between the different processes. And the context switch on a GPU is pretty expensive. Really, you can only have one process running at the same time unless you use different streams, which is not really implemented in Torch. Yeah.
So in Torch, there is a get device property.
Mm-hmm.
And I'm trying to understand, so the first field is PCI device ID.
Mm-hmm.
And no matter what set device I do, 2, 3, or whatever, that ID is always zero.
Always zero.
Is that what I should see?
Yeah, it's a little complicated. So is this on HPC?
No, this is on the K80.
On the K80? There is some level of abstraction happening at some point where the logical ID that's used in the actual for the driver is different from the Torch ID. And I don't really understand.
But if I'm doing set device 2, I'm going to logical device 2.
Is it working? Did you look at the memory it's using?
With the CMI thing?
You can use NVIDIA SMI. Yeah.
No idea.
Yeah. And then, for me, it's not been a problem so far. What's nice about this is if you do set device 1 and you're running on HPC, you're always being associated to a different GPU in like a virtual framework. And it will actually allow you to run on GPU 3 and treat it as like GPU 1. So on HPC, you only request one GPU, right?
Yeah.
But you're going to run on a node where there's 4 GPUs installed.
Yeah.
So how are you going to prevent everybody from using the first GPU device and only the third GPU device?
You need to pass the environment variable.
There's the environment variable, but you can also just use in Torch the first device. As far, yeah, as far as that.
But it's the same one.
It's somehow
Yes.
somewhat different.
And they moved, so the visible is what you actually get from the HPC, and then there is another
It's like the
parameter,
logical one.
which is just the storage.
Okay. I hope everybody is aware of like the interactive mode. You know, if you need a GPU when you want to prototype some stuff, you don't necessarily always know if things are working. Yeah, if you submit a job, right, and you get back the result, like you get the standard output, the standard error, and you see something is wrong, and then you submit another job until it works, is pretty key. So what you can do is you can request an interactive shell that lets you work on a node with GPU for an hour with the -I flag, in case you're not yet aware of it. And you should really make use of the data that's on Scratch. So the data on Scratch courses, unless you're creating your own data set, you can put it on Scratch as well. But for the deployment, you should really read the data that's in those folders. Does that make sense? Is it like very confusing?
The deployment, we're only deploying the model that's already trained, so we don't need any of it.
You need to test data, right? But so that's it, and that has to be written in from somewhere. Another thing I want to mention is that you should use floats, like you make it a float tensor before putting it onto the device, because supposedly the optimizations within the CUDA code are done for floats, single precision, not double precision. They just run faster. So if you work with double precision things, the CUDA the GPU makes it a little slower, as far as I know. Yep.
Sometimes I get an error that says CUDA runtime out of memory,
Mm-hmm.
and before I even start running the training procedure,
Okay, that means that you're loading too much stuff on your device. So if your entire training data is on the device, for example, that's probably already going to take up everything.
so I already have too much data.
The model may be too big. Yeah. Or someone else is running on it. But you're on HPC, right?
On the KD.
You're on the K. You make sure that there's someone else running on the device that you actually end up using.
How do I tell?
NVIDIA SMI.
Yeah.
Yes. Okay. Any more questions? Alright, I'm just going to go through the paper one by one, just like a few things that I think are important. I want people to know this. So the first thing is the tutorial in energy-based learning. And basically, I'm just kind of taking out of these papers what I think you guys should, at this point, have understood or have a pretty good grasp on. And the very first thing in the energy-based learning paper is just what is a model. You know, understanding the way they define it, or it is defined. And if you go to page 3, it really comes down to this thing. So what does that mean? You can think of E as a function that tells you how compatible two things are. You don't necessarily have to think about a function that, fitting a function that takes X and produces Y, but it's good enough to think of a function that tells you, given this X and given this Y, how much do they like each other? And they use the terminology of energy, which probably comes from physics, and they say a state has low energy if the things are compatible. So for example, if I have a picture of a car and I have the label car, then I want my model to associate low energy to those two
fix. If I have a picture of a car and the label of a dog, I want the model to associate high energy with those things because they're not compatible. And what you're doing when you're specifying a model, like when you're building these things, it's like you are sort of creating a space of like these energy landscapes that you then select from. So that's the next, that's really the next point. Over here. So W is going to be a point within this, you can call it hypothesis space, or finding the best energy function in a family of energy functions. The weight matrix, the particular weight setting is selecting a particular model. And then the way you do inference, there's a difference between inference and learning. The way you do inference from that model is by giving it a particular X and finding the Y that has the lowest energy. So if you have a correct model, then it's going to associate the lowest energy to the correct label. Right, that's what you sort of ideally want to do. Here's some examples. So the nice thing about this formulation is that like a lot of things can be expressed. So you can think about denoising. So you have like a noisy version of an image, and you have a less noisy version of an image, and you can think about the correct label being the denoised version of that image. So the lowest energy would be associated to the label version. Or you can think about the image of handwritten something, and then the actual text, the correct label, like the one with the lower energy, should be associated to the corresponding text. Or face recognition, or this labeling stuff here. And you can express within this framework different things. Prediction, classification, ranking, detection, and so on. So ranking, for example, is one of these things where you wouldn't necessarily just go, you wouldn't necessarily be interested in what label has the lowest energy given this X, but you would be interested in what's the ranking of the labels. Give me all the energies across all these labels. So your model needs to be able to give you an energy for every sort of configuration. You give it an X, you go for all the possible Ys, and you get a ranking. You give it an X, you take the lowest Y, you get a classification. Right? You take a Y and an X, and you say, is that what it is? You just look at the energy, and you compare it to the lowest energy. And you can say, okay, this is not the lowest energy, right? This is not the right thing. So I take a label that says a particular name, and I put in the face, an image of the face. And now I'm asking, is that guy in the image? I would look at the lowest energy label that's associated with this image and the energy of the label that I just gave it. And if they're not compatible, then I'm not detecting. Or I can also do partitional density estimation. And you see energies are just like these values, right? It's these functions, they're not really not necessarily bounded and whatever. But using the Gibbs distribution, you can go from energy to actual probability. And this should look pretty familiar to you guys, because it's a sort of soft math function. Instead of an integral, because you have a discrete domain while you're doing the summation. But integrals are also different applications. Okay.
And then the next thing I want you guys to understand is really what a loss function means and what a learning function means. So when I have these things here, these models, like these energy surfaces, and I have a training data right here, right? Those are like the two components that I have. Then I'm also need to have some way of selecting from the family of energy functions which model I like, and I also need to have something that tells me how good is this energy function that I selected. So gradient descent would be the way of selecting it, and mean square error would be judging how good is this. if that makes sense. So you would get these 4 components that come up in every learning scenario. Let me just see if I can find this in here. Right there. So you get the architecture, right? This is like the model part. So this is the stuff that you put into NN sequential to some extent. Then you get the inference algorithm, which in our case, most of the time is just argmax of the output, right? So we have our vector of probabilities, and we just predict the class that represents the highest index. So that's our very simple inference algorithm. Then we have the loss function, which in our case is a negative log likelihood for the last 2 assignments. So that tells us the, likelihood of the data set with respect to our given model, and we try to select the model that has the highest likelihood. And then we have the learning algorithm, which for most people has been SGD. So that's just gradient descent. So these 4 things, you can, in this framework, you can replace any of these 4 components with something else, and everything becomes modular like that. So you can think about creating your own loss function or creating your own learning algorithm and making and borrowing from ideas, like certain ideas from other concepts. So to give you an example of that, what I mean by this is within this framework you can express a lot of things that come up in other areas of machine learning. So for example, regression, right? Just regular regression. The energy is defined to be a matrix, like this GW function. It's just a matrix multiplied with X. Oh, sorry, this is the energy function, functional. Yeah, that's right. And the compatibility is how close is your projection into your, like this is what this GW gives. How close is your projection into the Y space with the actual Y label. Regression is like numerical values, right? And you can think of a matrix as taking a vector and projecting it into its own space. It gives you a value. And then this loss here, this is the squared error that we usually used to. It goes over the entire training data set and gives you a way of choosing W. So you can sort of see these components in here again. And the nice thing is that you get losses from the perceptron algorithm or the hinge loss, which comes up in SVMs, or you get the negative log likelihood. Or you can even go further down and you'll see other more complex models being expressed in this. So non-probabilistic factor graphs, which is something you wouldn't, like it sounds like it's something that you can only use for neural networks, but you can also apply graphical express graphical models in this framework. And I guess it's kind of like a little bit of a unifying theory to some extent across different ideas, and it's a principled way to talk about learning. So I really, really encourage you guys to like read through it and get a good understanding of what's being said in this paper. More or less from like a clarifying way. Like to me, it just sort of lined up many algorithms and gave me a bit more of a framework to think in. Okay, so then the next thing I wanted to talk about from the efficient backprop paper is really just the beginning. So I know there's like a lot of second order optimizations in that. There's a lot of talk about conjugate gradient descent and BFGS and these kind of things. And you can use them, and people have used them in practice. And I wouldn't, necessarily discourage anyone from trying them once you have everything else set up. But they are definitely non-trivial and takes a lot of time to make them work. All right, so what I'm trying to do here really is link up the stuff that's said in this paper with what you see in the code. So when you do the stuff in the code, how does it actually relate to this map? All right, So we have this picture over here, and then we have these equations over here, and it's kind of like, to me, it's been always a little bit confusing. So what I'm trying to do is now just go through like a simple example, and also related to the code. And this kind of also links back to the energy-based learning framework to some extent. And it's also pretty close to what Tom talked about last week in his tutorial. And I think his tutorial is a good way of understanding this a little bit better. So this is supposed to be a simple example, three-layer network, and I'm trying to do optimization on just one data point. So I just have x naught and the corresponding true label x3 hat. So this notation is strange, right? Because like usually these, to me at least, the subscript would mean like dimension 1, dimension 2, dimension 3 of a vector and so on, but you just have to sort of deal with it because that's how it's written in the paper. And what you're trying to do is you're trying to minimize this, right, overall. So x3 here is f applied to y3. F is just your regular nonlinearity. It could be a sigmoid, could be a ReLU, could be like a tan H or whatever, just like some nonlinear function. And I think what's interesting here is like what happens. So let me just like write out basically what E is. If you write out everything, is this visible a little bit? Yeah. So you can see here I have x0, and then these are all linear layers. So this is like n dot linear, right? So how have I built this? I did nn like add n dot linear, add n dot ReLU, add n dot linear, and so on. Like I added these 6 different things. It would take x0, take w1 multiplied by it, apply the nonlinearity to every vector, apply w2, apply the nonlinearity, apply w3, and apply the nonlinearity. And then compare it against the output that you want to see and calculate the squared error. So now the question is, how am I going to make E as small as possible? How do you make any E as small as possible, right? And what the thing is, what the optimization problem is like trying to find the extreme value of this, specifically the minimum. So how do you find extreme values of functions? Usually you take derivatives. And the only thing you can change about your model in this particular setting, like this is your model, and this is not the energy. So the energy would be, I say, the energy should be this entire thing. And the loss functional is taking this over your entire data set. You would calculate across the entire data set. It's like a little bit of a subtle difference. But this gives you a compatibility. How compatible is like x0 with x3? And it's dependent on what you choose y1, y2, and y3 to be.
What are those functions?
So you would then define an L to be the sum of E does that make sense?
Yeah.
So you would, instead of like trying to just optimize this one thing, you would not optimize this. You would try to optimize this here. Okay, so to be a bit more rigorous, I guess, in our case, because we only have one data point, L is just going to be x naught, x3 hat. That's it. Very simple example. And then we're trying to minimize the loss. So we take the derivative. And there's only a few things we can really take the derivative with respect to. The data set is fixed. x0, x3, that's given. You can't change anything about that. F are not parameterized. They're just functions. And the only thing we can change that really has an impact on like how our energy, how our model behaves, are these W's. So what we want to find is, the derivatives W1, W2, W3. Now, if all these F's were linear, right, if there was just like identity functions, if they didn't do anything, then this whole thing would just be W2, W3, W2, W1, X naught. And you could subsume all these into one matrix, and it would just become like a simple projection. And you can definitely find the optimal matrix over given your data set. But because of these nonlinear functions, it's actually very hard to come up with an analytic solution. It may sometimes work. Like you could actually, instead of doing backpropagation, write out this thing, take the derivative, find the extreme point, and find the analytic best weight. But you have to write so many equations, and you have to do it over the entire data set. And it wouldn't work for some nonlinearities that are destructive in some sense, like that are a many-to-one mapping. And very quickly stops working if you use like ReLUs. So we just find these gradients, and what do we do with this? So what does this mean? It means how does your loss change with respect to W1? But W1 is a vector, right? So how does, or it's actually a matrix. So we want to find these sort of three matrices. And then what do we do with these matrices once we found them? It's going to tell us how much does the loss change if I change this one particular weight entry in any direction, just from a linear standpoint, right? That's what a derivative is. So you don't want to go into the direction where it's going to increase. You want to go in the direction where it's going to decrease. So this is why we apply a negative in front of the learning rate. This is why we subtract the gradient, because you don't want to go in the direction of the steepest descent. You want to go in the other direction. You could do other things as well, instead of going in the direction of steepest descent or against it. But yeah, maybe you can come up with like a different heuristic or something. Because one of the key things is also, just because you minimize this, and just because you actually find the W's that do really well, doesn't mean that your function is actually going to generalize. So there's a difference between the optimization problem and the generalization problem. Getting zero training error doesn't mean that you're going to get zero testing. So this is just the optimization part of it. All right. So how do you find these things? You just apply the chain rule, right? And the chain rule is really like one of the key things for this entire derivation. So if you're trying to find this, and okay, as a warning, this notation isn't 100% mathematically correct. I'm going to write it out like this, and I'm going to sort of expand on it a little bit more later on to make it more precise, but I think this just gives you some intuition. So x3, as you remember, is the input from the layer before, and then this is a function composition, x3, x2, x2, x1, and then x1, w1. And you see these things here, they kind of come from above, if that makes sense. This has something to do with the things above you. Like you can't know here, you can't know this value. Only x3 knows how it responds with respect to x2. And these things will be given to you as like grad output from above. And you will calculate this value for yourself and then multiply them together, matrix multiply them together, and get your derivative with respect to the weight. So the derivative of the criterion with respect to the weight, and apply the change. Okay, so in the code, in general, what a module has is this backward function, right? So when you look here, you do a forward, you do a criterion forward, you do a backward, and you do another backward. And a module has as properties grad input, which is defined, so you can actually look that up. The gradients with respect to the inputs of the module. What they really mean is the gradient of the loss with respect to the inputs that come into the module from below. So this is what grad input stands for. And then output is just the last thing you output. Like it, instead of pushing these things through and then forgetting about it, you store them into a variable that's associated with your module. Because sometimes, for some modules, actually quite frequently, you need the output in calculating the gradient at a particular point. Okay. So you can see it just calls grad, update grad input. So update my own gradient with respect to my input based on what's coming from above and store it. And then accumulate gradient parameters, which means calculate the derivative with respect to the weights and apply them to my weights. These are the two main things that any backward thing does, right? And you can kind of relate that. So if you then go into the linear module, you can see it takes the grad output here and it multiplies it with the transpose of the weight. And if you go in here, you can see that this is exactly this equation. So the math that's being sort of written out and worked out on a module basis is then going to get applied right over here. Okay, and then the next thing that's mentioned is, I mean, this is like the easiest step that we can think of, right? We take the last weight vector and we subtract from it this derivative. So if you look into the code, it is actually doing it within optim SGD. Right here, x are the parameters, takes the learning rate, it doesn't add, multiplies the derivative and just adds it to it. So this is like the simplest update mechanism you can think about. But what it doesn't take into account is the second derivative, the second order derivative. It doesn't think about how quickly is my first derivative changing at this point. So it could be that you are at a point in your function or in your model, in your optimization procedure, where you could actually go much further in a particular direction. But because of the fixed step size, you're not making use of that. And there's a nice picture in this paper that gives you some ideas of that. Right. So if your learning rate is too big for a particular weight, you're going to go sort of over the bounds. You're going to bring your weight vector in a configuration where it is actually worse than where you currently are. And then you are at this, so if it was a parabola, you would be at this new point, and you would just keep on going back and forth. Right over here. So you see, if your learning rate is too big, you diverge. And second order methods, the idea is that you would take the curvature into account and you correct for that. And one way of doing it is to say, okay, right now I'm going to approximate my function by a quadratic function. I'm going to say it kind of looks like a cone, and just assume that I can apply the inverse Hessian to correct for that. But it's still an approximation in that sense. Let me just find the line.
If you're using the inverse Hessian, is that still considered gradient descent, or is that like Newton's methods at that point?
It's Newton algorithm. I mean, it's still always gradient descent to some extent. You're taking your gradient and you're putting it through the Hessian. So what you're trying to do is you think of your weight space, like you think of the value of your loss with respect to the weights of your function. And so, okay. So if you're over here, and let's say, yeah, it's not really nicely drawn. And let's say this was a higher loss value. Your derivative is going to tell you probably to sort of go into this direction, to the lower loss value. But if you knew exactly how far you could step into this direction, you could actually take this, let's say it was slightly slanted, and you could extend it to go all the way right in the middle. You know that along a certain diagonal, you can actually along a certain dimension, one of these W's could have its own learning rate that's much bigger than the other W. And that's what this inverse Hessian helps you with. But it assumes that you have a cone to some extent. And that's not always the case. So that's why sometimes actually, even though it's better for your optimization problem, even though you get better optimization performance, you get possibly worse generalization performance. That makes sense, yeah. Okay. So even though you get better optimization performance, you may not get better generalization performance. Better optimization performance means you have a lower training error, right? Okay. Oh, sorry. Okay.
It means that you'll get closer to the critical point, to the extreme point, but you will lose generalization. Okay.
Possibly, yeah. Those are two different things. Yeah. Okay. And then the other things I think are important to understand are, the point of normalization and of shuffling your examples. So why do we normalize our data, and why do we shuffle our data? And that's really also talked about in this paper. You know, some of the things, because it's from '98, are semi-outdated. Like it would still talk about sigmoids, whereas as we know, ReLUs in practice better, and so on and so forth. But definitely reading at least through the beginning of it, you will get an understanding of why it's important to normalize and shuffle your examples. So with respect to that, shuffling your examples. It's really just one sentence. So there is no simple way to know which inputs are information rich. However, a very simple trick that crudely implements this idea is to simply choose successive examples that are from different classes, since training examples belonging to the same class will most likely contain similar information. So you want to expose your network to different examples, because the gradient you're going to get is more likely to be at a point with extreme curvature, and you can possibly use a bigger learning rate to some extent. Does that make sense? Yeah. So you want to shuffle the training example so that they don't really belong to the same class. And you want to present something that produces a large error more frequently, because it actually gives back gradient and has more meaning. If you're already at a point where you're doing well, then yeah, you're stepping into directions where nothing changes. And the next thing is transforming your input. So why do we do the mean subtraction and the standard deviation division? If you initialize your model, I'm sorry, I'm going over time. If anybody has to leave, they're welcome to. If you initialize your model to be around 0, and you take your entire data and you send it to be around 0, then your model initially produces values that are kind of around 0, right? So you are already semi-correct, at least in terms of the mean. So these kind of normalizations already help. And the next thing is if you are normalizing your standard deviation across the variables, you are somewhat decorrelating the variables. So there always is some kind of correlation between variables and images, right? If you were to have a low-dimensional representation, or just like any representation of the image where the variables were perfectly decorrelated and they would absolutely represent what's in that image, then you could possibly just put a linear classifier on top and be done with it. But what people do is, they do PCA, where they use the maximum variance across the dimension as like an idea of decorrelating the variables and trying to find but these are just first order, like linear correlations that you're looking at, because PCA only looks at the covariance, right? And the covariance is a linear function. So it doesn't look at the square of one variable and the other original variable and the difference between them. So PCA only decorrelates on like a linear level. And these decorrelations can help you more quickly find meaningful models. So this is also explained in this paper a bit more. Okay. All right, and then from the convolution paper, really the main thing, I think that's important over there, is to some extent like the introduction to what a convolution is and why it's done. So I would really just like read out this paragraph, unless you guys rather prefer and read it at home. Yeah. So if you just do a regular fully connected layer, like you wanted to learn a convolution, what you would notice is that many of the weights are kind of replicated, and they're sort of similar across a network. And with this convolution operation, you are saving out on this weight replication because you just have this shifting window, the sliding window that you apply. Yeah. And at the same time, you also don't have invariance with a normal linear fully connected layer. So if you were just sliding across this pattern, this like small window of weights, what you also get is that the next layer will tell you whether this pattern has been, representative in this area. Like the inner product between the filter and the corresponding area tells you how compatible, like inner products in general sort of tell you how compatible two vectors are. So if you get a high value, it means that this pattern has been represented in that area. And in that sense, it gives you a little bit of invariance. Instead of like applying it as a big matrix multiplication, it just tells you whether it's present or not. Okay. And I think, so you can really see here that the network in figure 2 contains 39,000 connections, but only 60,000 trainable free parameters. So that's really the main thing with convolutions, is that you cut down on the number of weights that you have to train. Whereas your model is technically less expressive, you are restricting your energy space to models with functions that you think are more appropriate for the task. And the kind of function that you chose to be applied in the first layer has been kind of inspired by biology. But it's not necessarily that the function that you're using in the first layer has to be like the best function. You can come up with other things as well. I guess an example would be like these capsules, whereas instead of going for invariance, you're going to some extent to equivariance. So if you guys want to see like research in the direction of this, I recommend just briefly looking, not spending too much time, but briefly looking into this paper to be exposed to something that's different from a convolution and different from a just regular linear layer. And then what pooling does is it takes these kind of indications of pattern being present in that area and it averages across it. So it reduces your variance again. I think you guys have seen it in class, right? Like there was like this animation. He has it on his homepage as well. This one. So you can see as this number slides through, right? These are the first layer feature maps. So it would take this corner up here, the first convolutional layer, and produce this very top value. And the sliding window just goes through like this. And you can see that the change to the input is still represented as a change in the feature maps. But it's a bit more robust to variabilities. So this 5 here has a gap in the top, like you can see it over here, right? And when you look at the 5 over here, 1, 2, 3, if you have to sort of look quickly, you see it doesn't have a gap. And that's because you're not interested in like, is there a gap or not, but how compatible is this area with like the filter that would probably be just a line. Does that make sense? Yeah, maybe. And then you do pooling to get these smaller things. So it's even less invariant under, and you do another convolution, and now you get these small vectors. And you see that they're they're still changing, but they're changing less and less with respect to where the digit is in your image, and more whether there is a digit in your image. So it becomes more about what patterns are represented in it, and less about where are these patterns. It takes some of the locality out of it in stages. Okay. Anything? Do you guys have any questions with respect to like the assignment next week when it has to be handed in, and so on? Is that clear? What kind of deployment you have to do, and are there any problems with respect to that? Is it clear like what I want, what should be done, what is important for the assignment?
It's all posted online.
Huh?
It's all posted online somewhere, right?
Sorry?
It's all posted on
The handout?
website.
Yeah.
Right, all this information.
You mean the hand-in instructions? Yeah, it should be in the handout, and also some some sort of clarifications on Piazza. Okay. So that's really everything I wanted to talk about for today. I hope it made some sense. Yeah.
Sorry, can we submit code assuming that everyone can run like that.io or
Oh, I see. Well, you can call your own binaries from your home directory, right? And you could have mat.io installed in like your local install if you just set the access permissions. Does that make sense? No, we can talk about it later.